All right, so now we're going on to rational exponents part 2. So this is the second half to our lesson 5. And right away, what we're going to be presented with is our table of all our exponent laws. So the multiplication rules, division, power rule, zero exponents. We know multiplication is our product, division is our quotient. So this is a nice table to have, especially when you're going to be studying. I would like you to have this as a copy right next to you, whether that's taking a photo of it and just putting it off to the side or whatever it may be. Having these rules at your disposal, especially when doing problems, is really important here. Now, as a review of the last lesson, or 5a, when we looked at our exponential form, we realized we can also convert this in terms of radical form. So if the exponent form or exponential form is written on our left-hand side, which we'll denote as expo, then our radical form is going to be our form on the right-hand side here, radical form. Now, we need to look at these exponents and specifically say, okay, how do we go from exponential form into our radical form? Well, the exponent gets certain placement when we go to our radical. So we know that our piece here, our n value or the denominator of our exponent, that was actually labeled as our index value. So we say this is our index. Our m value was our power or our exponent / exponent. Now, I want you to realize where these are assigned from. Our denominator of our exponent goes into the index as such. So our n from our denominator of our exponent or our rational exponent ends up going and being the index, whereas our numerator becomes the power, which can be written two ways. We can write it either outside of the brackets or outside the radical, or I can write it underneath the radical and connect it to whatever the base is. Either way will give us the same solution, and we're actually going to see why this is important to distinguish that it could be either or. Now, let's go below here and look at a couple examples. They say simplify the following rational expressions. Write as a power with a positive exponent and then as an entire radical. So we want to first simplify these in terms of powers and then see if we can convert at the end. Now, if we're looking at example 1, I immediately go, well, if nothing is written in the power of this y, I'm going to write it as 1. So by product rule, we know we keep a common base, which in this case is y, and we add the exponents, so 3 over 2 plus 1. Now, from our number sense unit, we knew that before we add any of these, we actually have to create a common denominator. The lowest common multiple, or our common denominator in this case, comes from if I multiply my right side by 2 over 2. If I have 2 over 2, well, that's simply just 1, but it allows me to scale this such that I can create a common denominator. So I have y is equal to 3 over 2 plus 2 over 2. And now we know 3 over 2 plus 2 over 2, that's going to be equal to, this is going to be equal to y, 5 all over 2. We do not change the denominator in this case. Now, if I want to take this from exponential form into radical form, I'm going to have to start by writing my radical symbol, y, which was the base, and then assign these. We know that my 2 from the denominator of my rational exponent goes out front of my radical. Now, the reason I'm not going to write it here is that 2 doesn't get written here because we automatically know if nothing's written here, our standard square root actually implies that we have a 2 in our index. So we're going to leave that out. And now I'm going to assign 5 into the power spot. And I can rewrite this in terms of, well, what if I have the radical with the base, and then I multiply, or I have the power outside of it all? That would be totally fine. These are congruent, which means they are equivalent statements. So both of these are correct. These are both congruent statements or equivalent. All right, let's go over to example 3 here. So example 3, we identified that this is the power rule. We have a to 1/2 raised to the 3 over 2 here. So we know we have a power next to a power. This is going to create a multiplication or the power rule. And how we're going to handle this is we're going to say this is equal to a, which is the base, 1 over 2 times 3 over 2. Now, the nice thing about the power rule here is it results in multiplication, and multiplication doesn't require a common base. So I'm going to multiply across the numerator, multiply across the denominator. That means this is equal to a to the 3 over 4. Now, 3 over 4 won't reduce, but what I can do is now make this into radical form. So this is equal to, I start by writing out my radical symbol, a, and now I want to assign the denominator into the index spot so it becomes 4, and then I assign my numerator, which is the 3, into the power or exponent. And remember, this is congruent, or can be also written as the 4th root of a, all to the power of 3. These are congruent statements. They are equivalent. You would get the same solution for any given a. All right, let's flip the page over and we're going to look at example 2 and 4. So example 2 starts with an x to the 3rd divided by a 5 over x to the power of 5 over 3. In this case, we know division means we have the quotient rule, and we're going to subtract our exponents. So this is equal to x is the common base, 1/3 minus 5 over 3. Now what's really nice here is we know that it's already a common denominator, so I can go x, 1 minus 5 is going to be -4, and this is over 3. Now, in order to convert this to radical, remember, first we want to have positive exponents, so this is actually equal to 1 over x to the positive 4 over 3. We do the reciprocal of the base and make the exponent positive. And now I can say 1 over the radical symbol of x. Now I want to say my index is whatever's in the denominator of the power, which is 3, and my power gets attached to my base value. And this is also equal to 1 over bracket the cube root of x bracket all raised to the power of 4. Those are equal statements here. All right, let's go over to example 4 now. Example 4, there's a couple ways we could do this. We could apply the power rule and distribute right away, so I could take 1 negative 1/2 and distribute it to both. However, what I'm going to do is I'm going to say, I have this negative in the exponent. What does that mean I do? Well, I'm going to take the reciprocal of whatever the fraction is and say y over x squared, all raised to the power of a positive 1/2. I've done the reciprocal of whatever the base is, and now I have a positive exponent. Now, if I want to distribute this, I know y has a power of 1 and x has the squared. Okay, so now when I distribute this in, when I distribute the 1/2 to both of the exponents, let's see what we get here. So this is equal to y to the 1 times 1/2 is 1/2 all over x 2 times 1 over 2. That means we have this is equal to y to the positive 1/2 over x 2 times 1/2 is just 1. And now I have to convert this into radical form. That means this is going to be root of y. I assign my index value as the denominator. Well, remember, if it's 2, we automatically know that we don't have to write a 2 here. It's not necessary. I mean, we could, but we're just going to leave it out. And then we have a 1 power from the numerator here. Do we need to write that? Not really, because anything to the power of 1 is just itself, and this is all over x. Therefore, this is our solution here. All right, let's move on to example 5 here. So if I go down to example 5, I immediately recognize I'm multiplying two things with a base. So I have 3 times 5, and they're not attached to exponents, so this is equal to 15. And now by product rule, I have x to the 3 over 4 multiplied by a -2. That would be doing power rule. I want to make sure I add these because product means we add. There we go. So I'm adding the exponents in product rule. Now this is equal to 15x. I have to find what is the LCM of this, or what is the lowest common multiple between 4 and 3, because we need a common denominator. So in order to get this common denominator, I realize that 12 is what I'm looking for, and I have to multiply my right fraction by 4 over 4, and my left fraction here by 3 over 3. That gives me 9 over 12 plus minus, we could actually say this is a negative. A plus minus results in us subtracting. Subtract 2 minus 4 is 8 all over 12. Now finally, this is 15x to the 1 over 12, or 9 minus 8. Okay, now our final step is to make this into radical form. The 15 is not attached to the power. We put the base under the radical, and now we take the denominator of our exponent or rational exponent and put that as the index. So I put 12 on the outside, and I could put a 1 here, but anything to the power of 1 is just itself. So I'm almost just going to leave this and call that our solution here. All right, jumping over to example 6. Instead of multiplication and having the product rule, now I have the quotient rule. This is equal to, well, the 25 and the 5 do not have any connection to our exponents. So we can use standard division here. 25 over 5 is 5. And now I'm left with x to the, well, these exponents are going to be subtracted because we have the quotient rule. 3 over 5 minus a negative 5 over 3. Yet again, we're thinking, okay, we have to make an LCM here. So the lowest common multiple between 5 and 3 is 15, meaning I have to multiply my left hand by 3 over 3, my right hand by 5 over 5. This is equal to 5x to the power of 3 times 3, which is 9, over 15. A negative and a negative are going to combine to make a positive. So we can actually convert this into being a plus 25, or 5 times 5, over 15. Now this is equal to 5x. 9 plus 25 is 34, over 15. And now what I can do is say, can I reduce this fraction? You always want to look at a number like this and say, is it reducible? Or can I make it in a lowest terms here by dividing it by some form of common number? Well, 34 only divides by 2 and even numbers. 15 divides by 3, 5, 15, and 1, which are all odd numbers. So if 34 only divides by even and 15 divides by all odds, we know this won't reduce anymore, and now I can just go right to my radical form. The 5 isn't attached to the exponent, so I can write it again, and I'm going to put radical symbol, our x value, or our base value, and then put 15, which is our denominator, in terms of the index, and 34 in the power. Now, an equivalent form would be to say this is equal to 5 to the 15th power, or 15th root of x, to the 34th power. So let me repeat that. It's 5 is a coefficient, 15th root of x to the 34. And these are equivalent. Whether you want to put your power under the radical or you want to put it outside the radical, that is totally fine. Either way, just be really careful with those brackets, making sure that your radical is all in a bracket and the 34 goes outside, or the 34 is connected to everything under the radical. All right, and then finally, example 7 here. Example 7 is power rule, and we know this because we have things inside the brackets raised to another exponent. Now, what is the exponent on 27? If it's not written on a number, it's always just equal to 1. And now we can use our distribution. We can distribute 4 over 3 to the 1/2 and 4 over 3 to the 1. This is going to be equal to 27 to the 1 times 4 over 3, which is 4/3, a 1/2 times 4 over 3. So our next step is 27, 4 over 3, a. By multiplication, I can multiply across the numerator, multiply across the denominator, meaning I have 4 over 6. Now here's where we have to be really careful. Even what we were doing on the previous example, example 6, we want to check and see if we can reduce our rational exponents. In this case, 4 over 6 can definitely reduce. So we want to rewrite this as 27 to the 4/3 with a to the 4 over 6 reduces by 2 each to be 2 over 3. Okay, this is interesting because we have index values or bottoms of our rational exponents that are equal. Meaning what I could do is I could say this is equal to the cube root of 27 to the fourth power a to the second power. That would be totally valid because they share the same index value or share the same denominator of the rational. However, I'm going to break these apart because what I want to try and do is simplify this 27 as much as possible. So this is equal to the cube root of 27 to the fourth power multiplied by the cube root of a. And we can put the squared underneath or outside. However, why I wrote the 4 outside instead of underneath the radical like so is that this is actually going to be a lot simpler. If instead, what if I put the 4 under the radical here? Well, what would happen is we would have 27 to the fourth power, or 27 times 27 times 27, and we'd have to cube root that. And we do have our calculators, so that's okay. But what I would rather do is see if we can do something that we can use mental math with. So this is equal to, well, the cube root of 27, or 3 numbers that multiply together that are the same to make 27, would be 3. If I do 3 times 3, that's 9, and times 3 is 27. So I can convert the cube root of 27 to be 3, and this is raised to the fourth power. And then we have the cube root of a squared. Our final step is to just say, what is 3 to the fourth power? Well, that's 3 times 3, which is 9, times 3, which is 27, and then times 3, which is 81. Or off to the side here, I could write 3 times 3 times 3 times 3, which is 9 and 9. And if I multiply these together, that is going to be 81. So we can do this. We can write it out or expand it out and simply just use our mental math to get this solution of 81 to the cube root of a squared. And this is our solution here. All right, now it's your turn to practice, so check your understanding for these. There's lots of practice problems.